This begins the first part in this two-part series on the second law of thermodynamics. The second law of thermodynamics has been contemplated by scientists as well as philosophers, for that last 150 years or so. It forces inescapable and often depressing limits on what processes can and cannot happen in our universe. For historical reasons, there are many ways in which the second law of thermodynamics has been stated throughout the ages. And we'll explore these different forms of the second law. In this video, we'll talk about heat engines and an expression of the second law of thermodynamics in terms of them. But first, let's take a look at how the limitations inherent in the first law of thermodynamics gave rise to the second law of thermodynamics. So like I said, we will start by reviewing the first law of thermodynamics. And remember, in a previous lecture we said the first law of thermodynamics is really nothing more than a restatement of the law of conservation of energy, for thermodynamic systems. Let's take a look at some examples of physical processes that obey the first law of thermodynamics. Like Lake Don Pedro freezing over on a hot summer day. Or the test tube that you drop spontaneously reassembles itself, and rises upwards into your hand, unbroken. Or how about this one? Your messy bedroom spontaneously rearranges itself into a paragon of order. So, you're starting to see a little bit of the problem, and why we need the second law of thermodynamics. None of these processes that are described here in these three examples violate the first law of thermodynamics. They are all consistent with the first law of thermodynamics in that energy would be conserved in every single one of those processes, yet they never actually take place. The second law of thermodynamics is necessary to tell us which processes that conserve energy spontaneously occur in nature. So as I was saying, one of the ways in which the second law of thermodynamics has been stated, one of the first ways, was in terms of heat engines. And heat engines in the mid-1800s were a prime focus, kind of as a precursor to the Industrial Revolution. A lot of study was done on them, and this included from a scientific perspective as well. So a heat engine, really by definition, is any device that transforms internal energy or heat into mechanical energy. Said simpler, any device that converts heat into work. So some examples of heat engines, one we looked at was the thermoelectric converter. If you think about it, this is a simple heat engine, that uses the flow of heat from a high temperature reservoir or cup to a low temperature reservoir, and in the process is able to get some work done that you saw on the fan motor. Obviously, the internal combustion engine of an automobile, is the most common and important example of a heat engine, in contemporary society. And we will talk more about those later in this, in this video. And a steam engine, which was another big mover and shaker in the Industrial Revolution. A device that can convert hot steam, into mechanical energy. So in order to formulate a statement of the second law of thermodynamics in terms of heat engines, we need to start by discussing the thermodynamics of the heat engine. In other words, we need to take a look at what is going on inside of any heat engine in terms of energy flow, and work being produced. Now, there's many different forms of heat engines, and I'm showing you kind of an example over here in the right-hand corner of your screen. And whether you're talking about an internal combustion engine or a thermoelectric converter or steam engine, the mechanical workings may be quite complicated and different from engine to engine, but the thermodynamics is all the same. So let's start there. Now, if a heat engine is a device that can convert heat into useful work, then we know that heat is really the flow of internal energy. So in order to get that to happen, okay, we must start out, in order for heat to flow, there must be a temperature gradient. So what I'm showing you here, this represents your high temperature reservoir, okay, and what I'm showing you here represents your low temperature reservoir. There must be a temperature gradient that exists in order for heat to flow. So T sub H represents the high temperature of that reservoir, and T sub C, okay, the low temperature, let's say the cold temperature of your lower temperature reservoir. Now, what we'll put here, this circle represents a system. Whether it's an internal combustion engine, a steam engine, thermoelectric converter, okay, or the silly contraption you see here on the screen, it just represents any heat engine, okay? It represents a system in general. And schematically, we can say that in order for any heat engine to work, okay, you must have heat that flows from your high temperature reservoir, okay, into your system. So I'm showing you with this arrow here, Q sub H represents the amount of heat that is leaving the high temperature reservoir. Okay, Q sub C represents the amount of heat that is entering the low temperature reservoir. So this is nothing more than heat flow. Notice here that the amount of heat entering the low temperature reservoir is less. That arrow is a little thinner than the amount of heat leaving the high temperature reservoir. Why? Because some of that heat gets converted into doing useful work. So while you see that this does not tell you how to construct a heat engine, this schematic diagram is true for all heat engines, okay? Because this is what they do. They capitalize or exploit the flow of heat from a high temperature reservoir to a low temperature reservoir, and in the process are able to get a certain amount of useful work done. So in this slide, we will take a look at the thermodynamics involved in a cyclic process. And by cyclic process, we mean any process that begins and ends in the same thermodynamic state. Now, if you look at a thermodynamic process that begins and ends in the same thermodynamic state, okay, when we look at the change in the internal energy for any cyclic process, remember that internal energy is a state function, which means that the internal energy only depends upon the current state of the system. So if our beginning state and our ending state, our initial and final state, are the same state, okay, then by definition there is no change in internal energy for, okay, this cycle or cyclic process. So we want to take a look at the work that gets done in a cyclic process and try to understand something general about, okay, the work done for any cyclic process. So in order to do that, we'll take a look at the specific example. In this example of a cyclic process, we're looking at a particularly easy cyclic process, an easy cycle where we have two isobaric processes, okay, as well as two isovolumetric processes, and we want to calculate the net or total work done, okay, for each process as well as the net or total work done for the entire cycle. So here are the specific numbers we're going to take a look at in this problem. And you'll notice here that if we start over here at point A, okay, and going from point A to point B, this looks like an isobaric expansion, right? A constant pressure, but our volume is increasing. And going from B to C, the volume doesn't change. The volume is 250 volume units, okay, but it looks like the pressure drops. So that would represent an isovolumetric process. And going from C to D, looks like the volume decreases, but the pressure is constant, so we can consider this to be an isobaric compression. And then in going from D back to A, we're once again looking at an isovolumetric process. So you can see here that this four-process cycle, okay, we begin and end at the same point on our PV diagram. So in order to calculate the work, okay, we know that, well, two ways. The work done for any process is simply the area under the PV diagram, but in the special case of the isobaric process, okay, the work that is done on the system, okay, minus integral of P dV, and for the isobaric process, since the pressure is constant, just minus P delta V. So from A to B, we have a constant pressure of 250 pressure units. The change in volume, we're going from 50 to 250 volume units. Okay, so 250 times 200 gives us an amount of work equal to minus 50,000 pressure volume units. You can see very clearly that there is no area under the graph from B to C. Okay, delta V is 0. There is no change in volume, so there is no work done for that part of the cycle or for that process. Okay, and going from C back to D, this isobaric compression, okay, the pressure is only 100 pressure units. Okay, once again, we're going from 250 to 50, so we have a change in volume that is negative of 200, okay, times 100 gives us, 20,000 pressure volume units, okay, minus PdV is 20,000. Once again, going from D to A, there was no change in volume, so there was no work done there. And when we calculate the net or total work done, by adding up the work done in each of these 4 cycles, minus 50,000 plus 20,000 gives us a total work done of negative 30,000 pressure volume units. Now, so that is done by finding the work done for each of the cycles and then adding up the work terms. But I want to show you here that the net or total work done by the system is simply the area enclosed on this PV diagram. Notice here, this is the work done by the system on the environment. Whereas the work we're finding here, this is the work that is done on the system by the environment, and that's what that negative sign is all about. So the area enclosed, in this PV diagram is really just the area of this rectangle here, which we can simply find. That's one of the reasons why we looked at these simple processes, because it's an easy area to calculate. So the length of that rectangle times the width. So our length here is going to be 250 minus 50. Our width, or I guess height, you might call it, is 250 minus 100. And the length times the width gives us 30,000 pressure volume units. Notice that this is opposite in sign from our answer here, because this is the net work done on the system here. That's why we have a negative sign. This is the net work done by the system, which we just showed is exactly equal to the area enclosed, on our PV diagram. General principle here we learned by solving this specific problem. So why, you may be wondering, are we talking about cyclic processes? Well, it turns out that when we talk about a heat engine, regardless of the type, it is an example of a cyclic process. Because, for a complete cycle, the working substance starts and ends at the same temperature. In which case, we can say that the change in internal energy, is 0 for this cyclic process. You also recall that we said that the internal energy for an ideal gas is directly related to temperature. So if we have a system that begins and ends at the same temperature, for an ideal gas at least, there is no change in internal energy for that system, for that reason as well. So when we apply the first law of thermodynamics to a heat engine, then we get 0 for the change in internal energy, and we find out that the work that is done on the system is the opposite of the net heat that is added to the system. When you take a look at your schematic diagram over here, you can see that the net heat added to the system, remember your system is taking in an amount of heat QH from the high temperature reservoir and expelling an amount QC to the low temperature reservoir. So given that, okay, the net or total heat that gets added to your system is just the difference between those two heats, that is QH minus QC. In which case, okay, we can say that the work that is done on the system is the opposite of, okay, QH minus QC. Okay, I will say that, and you remember me telling you a long time ago that the way the first law of thermodynamics was initially stated, it was stated as a result of work that was done on heat engines, in which case there was a sign when we talked about the first law, we stated it as Q minus W, because W was defined to be the work done by the system, not on the system. In fact, your textbook, until about 5 years ago, okay, stated the first law of thermodynamics this way. And I made a big deal out of saying that I like the current version because it explains what's happening from the system's point of view, okay, by saying that W represents the work that is done on the system, okay, in which case, that explained the sign conventions that we were using here. But here you can see that if work that is done on the system is negative, then work that is done by the system is positive. And so we will very often, when we talk about the second law of thermodynamics in terms of heat engines, I put here work, okay, engine, that this is the work that is done by the system, okay, because that's what heat engines are used for, right? They're used to do useful work, to convert heat into useful work. So in this case here, the work that you get out of your system, out of your engine, is a positive number, okay, because it is going to be work that the engine can do on the environment. And it is simply the difference between the heat that gets added from the high temperature reservoir and the heat that gets expelled to the low temperature reservoir. So how do you measure the efficiency of a heat engine? Before we talk about heat engines specifically, let's just talk about the efficiency, okay, of any machine. And when you think about it, why you tend to use a machine, okay, a machine is giving you some quantity out. Okay, in our case here for a heat engine, it's useful work. But regardless of the machine you're talking about, you put something into the machine, you get something out. And efficiency in general will be a measure of what you get out, okay, compared to what you put in. So when we talk about a heat engine, okay, it's work and energy that we're talking about. So we can talk about the efficiency of a heat engine as being a measure of the useful work, okay, that you get out of your engine that is done by the system on the environment compared to the amount of heat, okay, the net heat that gets added to your system. Okay, that's your input. So here, since we have expressions derived for this previously, okay, remember we said that, the work that is done by the system on the environment, the work you get out, the work of your engine is just the difference between, okay, amount of heat added from the high temperature reservoir, okay, and the amount of heat expelled to the low temperature reservoir. The heat that gets added to the system, okay, Q high over here. And when we simplify this here, Q high minus QC over Q high, we can write it a little bit differently using some algebra here. Okay, but this is an expression that represents the efficiency of any heat engine. So I will put this up from the previous slide. When we take a look at the efficiency of a heat engine, we see very clearly from this definition that if you want to increase the efficiency of your heat engine, okay, then it's this ratio of QC to Q high that you have to work on, right? As that ratio gets smaller, the efficiency gets closer to 1, or, okay, converting it to a percent, 100%. So here, making QC as small as possible compared to the amount of heat that is taken in from the high temperature reservoir, The smaller the amount of heat that is expelled to the low temperature reservoir, the more efficient your engine. Could you have a 100% efficient heat engine? What would that look like schematically? Well, this is what the schematic diagram would look like. You'll notice here that, okay, for an amount of heat Q high, which is extracted from the high temperature reservoir and enters your system, all of that heat gets converted into useful work. There is no expulsion of any waste heat to your low temperature reservoir. That is what a 100% efficient heat engine would look like. And, okay, remember we said that one of the ways of stating the second law of thermodynamics is in terms of heat engines, and this is a statement of it. There is no such thing as a 100% efficient heat engine. In other words, there is no device that can convert a given amount of heat completely into useful work. There will always be expulsion of waste heat to your low temperature reservoir so that Q sub C will never be zero. So this is, when you look at a physical law like this, notice that this is not derived from any previous principles. This is just a statement of reality, okay, based on observations, based on, experiments that are performed by scientists. Okay, we think of this as an observational law that you cannot have a 100% efficient heat engine. You must always have this transfer of waste heat to the low temperature reservoir. So a schematic diagram of a heat engine does leave a little bit out, okay, about reality. So in this slide, we'll take a look at a specific example. Okay, an example of a heat engine that is quite important to us, the internal combustion engine, and take a look at answering some qualitative sorts of questions. So first I'm asking you, what is the typical efficiency of an automobile's internal combustion engine? Now I think many of you may know the answer to this already, but if you don't, I think you'll be a little bit surprised by the answer when you see it here. A typical heat engine, typical internal combustion engine is only about 20% efficient. Diesel engines achieve a much greater efficiency because of their high compression ratio. And I will say that, this is a typical efficiency. I happen to drive a car that has a fairly high compression ratio too, so its efficiency is much greater than 20%. But, I think that result may be a little bit surprising if you didn't already know it. So suppose that the internal combustion engine in your car was 100% efficient. Okay, what would be physically different when operating your car? Well, certainly you would get much better gas mileage, right? About 5 times better if you drove the typical car, right? Since all of that heat that was extracted from the high temperature reservoir would go into useful work. Another really important difference would be that you would have no need for a cooling system in your car because your engine would never heat up, right? If you're not going to extract any waste heat to your low temperature reservoir, okay, if all of the heat that was taken in by the engine was converted into useful work, okay, there would be no waste heat, no need to cool your engine because, it wouldn't exist. And so, in a sense, when I say no exhaust heat, your engine would also be producing no thermal pollution to the environment, which would greatly help in this fight against global warming. So another way to state the second law of thermodynamics is in terms of heat pumps, okay, and or refrigerators. And we will see that a heat pump or refrigerator is intimately related, okay, to the heat engine. So let's start by defining what do we mean by a heat pump. A heat pump is really any device that transfers heat from a low temperature environment or a low temperature reservoir to a higher temperature environment or higher temperature reservoir. Examples of real heat pumps used in society, certainly the refrigerator, okay, is an example of a heat pump, okay, transferring heat from a low temperature environment that is inside of your refrigerator to the higher temperature environment of your room. An air conditioner, okay, another example of a heat pump. Uh, okay, transferring heat from a low temperature environment to a high temperature environment. Many home heating systems, okay, use heat pumps. This is not the only way, but it is one of the ways that houses can be heated. Okay, so we will talk about, in the next slide, how to represent them schematically, and we will come up with a statement of the second law in terms of heat pumps. All right, so let's talk in a little bit greater detail about the differences between heat pumps, okay, in refrigerators versus heat engines. And we'll actually start here with the schematic. So here we see the heat engine, and we know that when you allow heat to flow naturally from the high temperature reservoir to the low temperature reservoir, you have the possibility of getting some work out of your system, okay, some work that is done by the system on the environment. Here we have a schematic diagram of a heat pump or refrigerator, in which case we take heat and force it to flow unnaturally from the low temperature reservoir to the high temperature reservoir, okay, by doing some work on the system to make this happen. So the heat pump or refrigerator versus the heat engine, like I just said, a heat engine converts heat into work by allowing heat to flow naturally from the high temperature reservoir to the low temperature reservoir, while a heat pump or refrigerator uses work to transfer heat from a low temperature environment to a high temperature environment. So then what makes a heat pump different from a refrigerator? Well, it's really a question of perspective of what you want to use it for. Most households, for example, that use heat pumps will use a heat pump in order to heat the house, and they will also use a heat pump, okay, turned to a different setting to cool the house. So it really is a question of what is inside versus outside. So a heat pump is really nothing more than a refrigerator turned inside out, such that you're just exchanging the inside for the outside. So if you think about it, a refrigerator transfers heat from the cold temperature environment, that is from heat from inside the refrigerator, to the higher temperature environment of the room by placing the evaporator coils inside the refrigerator, while the condenser coils are located outside the refrigerator. So if you think about it, then a heat pump, it's exactly the same device, okay, but it is transferring heat from the cold temperature environment, let's say outside of the building, outside of your house, to the high temperature environment, okay, which is inside of your house. So the evaporator coils are located outside of the building, while the condenser coils are located inside the building. So like I say, it's the same device, and most of the times when a house has a heat pump in order to heat the house and as a form of air conditioner, you get a single device that performs both functions. But like I said, there are many other types of ways to heat your house. I mean, you can use, for example, natural gas, which you just combust to heat your house, and this is still a very common method of heating systems. But heat pumps are another form. The schematic is what we talked about right here. Okay, I'm just doing a little bit out of order here. So just like we did for the case of heat engines, okay, we're going to apply the first law of thermodynamics to heat pumps and refrigerators in order to get an expression for work, to figure out how much work must be done on the system here. And after we do that, we will also talk about the equivalent measure of efficiency. We don't call it efficiency, but it's virtually the same concept here. So let's start by applying the first law to a heat pump. And remember, a heat pump, a refrigerator, it's the same device. It's just a question of what you're using it for. Okay. When we apply the first law, just like for heat engines, a heat pump, refrigerator involves a cyclic process where, okay, our system begins and ends in the same state. So we can once again say that the change in the internal energy of our system, okay, of our heat pump or refrigerator must be zero, okay, which is true for any process. It begins and ends in the same state. In which case, okay, change in internal energy is equal to the heat that gets added to the system, okay, plus the work that's done on our system, so that must equal zero. And here, when we look at it, the heat that gets added, well, the net heat added, I should say, remember your system, your heat pump, takes in amount of heat QC from the low temperature reservoir and expels a greater amount of heat QH to the high temperature reservoir. Okay, so the net heat added is the difference here in this order, QC minus Q high. Okay, the work done on the system is W, right? You've got to put work into this machine to be able to unnaturally transfer heat from the low temperature reservoir to the high temperature reservoir. So here we can solve this for work, and we find out that work is just, okay, the difference between Q high and QC. So in other words, okay, an amount of work is done on the system that is equal to, okay, the difference between the work expelled to the high temperature reservoir, which is the heat expelled to the high temperature reservoir, which is the greater amount of heat, okay, minus, okay, what heat is withdrawn from the low temperature reservoir. So here you see this term here will always be positive, telling us that you have to do work on the system to make this unnatural process happen. So here, the work that the heat pump must do is the work done on the system. And I say here, notice that for the heat engine, we defined really two works, because the work that was done on the engine isn't really what you get out of a heat engine, right? You get work that is done by this system on the environment. So we came up with this other expression for work we call work engine. In other words, the work done by the system, which is exactly equal and opposite to the work done on the system. Okay, but here all I'm saying is that for the heat pump or refrigerator, it's got to be work done on the system that we're looking at. So there's no need to, change what we get out of the first law. So efficiency, we don't call it efficiency, but it's really the same concept. What we call it is a coefficient of performance. And if you were to go to Sears and buy a refrigerator, I guess not Sears anymore, at least there is no Sears in Modesto, and I don't believe in our country anymore. You go to Western Appliance, Home Depot, Lowe's, whatever, to buy a refrigerator, you will see the COP rating on that refrigerator. So it's a measure of efficiency. Remember we said that for the heat engine, the efficiency is a measure of what you get out compared to what you have to put in. Same concept here. Coefficient of performance is a measure of what you get out of your heat pump or refrigerator. We can call it gain, if you like, to what you have to put into it. Okay, so the coefficient of performance, it depends on whether you're using the heat pump in its heating mode or cooling mode. So here, there's really two ways to measure it. And you've got to measure it based on what you want to get out. If you're using a heat engine in its cooling mode, let's call that an air conditioner, your goal then is to remove energy or heat from the low temperature reservoir. Okay, so we would say the gain then, what we're trying to do is remove heat from your room at a low temperature. So QC is really a measure of what you get out, how much heat you're able to remove from your room compared to what you got to put in, which is work. Okay, so this ratio QC to W is a measure of your coefficient of performance, kind of like efficiency, when your heat pump is in its cooling mode. When you have your heat pump in its heating mode, ask the question, what are you trying to get out? Well, in this case, your goal is to actually use it to heat your room. So your goal, your gain, is really measured by the amount of heat that gets transferred into your high temperature environment. Okay, and that's Q high, once again, compared to what you have to put into your system, your machine, which is always work. All right, so in this slide, we will take a look at a specific example which will not only help us to see some of the differences between a heat pump in its heating mode and cooling mode, but I think you're going to learn something that might surprise you about the efficiency of a typical heat pump. So in this example, we're told that a heat pump is used to heat a house in a moderate climate by using an electric motor to pump heat from the cold outside to the warm inside of the house. This is what heat pumps do in their heating mode. Heat pump has a coefficient of performance of 3.0 and is rated to do work at 1500 watts. In other words, 1500 joules of energy transferred per second. Assume that the motor running the heat pump is 100% efficient, which of course is not true, but it'll make calculating this calculations here a little bit easier. First we're asked to calculate the quantity of heat added to the room each second. So we need to use our definition for the coefficient of performance for the heat pump in its heating mode. And remember, we said that it's a measure of, the heat, which is transferred from your device to the high temperature environment, Q high, divided by the work that your pump must actually do to make this unnatural process happen. So here, we want to find in the problem what Q high is. What is that amount of heat that gets transferred? So we're going to multiply the work, which we're given this in terms of power, right? 1500 watts or joules per second. If we want to find the quantity of heat added per each second, then we need to find the amount of work done in 1 second. So we'll simply multiply the power times the time of 1 second. So it gives us 1500 joules times the coefficient of performance. Tells us that in 1 second, 4500 joules of heat is transferred from our low temperature reservoir to our high temperature reservoir. Now, that may not seem so surprising, but we'll take a look at this follow-up problem here, and we'll take a look at another type of home heating system, which is just your electric heater, which you plug into a wall receptacle. And if it is a 1500 watt heater, it says if the conversion of electrical energy into thermal energy via an electric heater is 100% efficient, which it is, and you can convert a given amount of electrical energy, or work 100% into heat, which device should you choose to most efficiently heat your home? Explain. Well, your answer is right here. A 1500 watt heater will provide you with 1500 joules of heat per second. But compare that to the 4500 joules of heat per second you get with your heat pump. So think about it. When the electric heater is plugged into the wall, it draws 1500 watts of electrical energy per second and delivers 1500 watts of electrical heat per second to the room. The heat pump also draws 1500 watts of electrical energy from the power company in order to operate the pump, but it delivers 4500 watts or joules per second of heat to the room. Do you see that your heat pump is giving you 3 times the output, delivering 3 times as much heat for the same input of work? So it's a little bit surprising, even though that heat pump, that pump itself is not going to be 100% efficient. It is producing a whole lot more energy for your room than the electric heater, which is 100% efficient, which is converting all of that work into heat. So I say true, the real efficiency of the heat pump motor will not be 100%, but even at 90% efficiency, the heat pump is far more efficient than the electric heater. Of course, you've got to figure out the cost of installation, right? Heat pumps, as you see in the diagram here in the simulation, they have to be buried outside in your ground. So, an electric heater is it's a simple device and an inexpensive device in comparison. But your heat pump is certainly far more efficient. Now, in the last part of this problem, we're asked to consider the heat pump that is used in its cooling mode, used as an air conditioner in the summertime. So what would its coefficient of performance be? Okay, assuming that everything that we said in previous parts of the problem remains true. Well, okay, here we find out that, QC, the amount of heat which is removed from the cold temperature reservoir, okay, plus the amount of work that is done by the pump will be exactly equal to the amount of heat which is, okay, then extracted to the high temperature reservoir. So, given this, solving for QC, okay, Q high, we know that we are, from our previous problem, okay, moving 4,500 joules of heat from the low temperature reservoir to the high temperature reservoir. So Q high is 4,500 joules. And we know that the pump itself, okay, is a 1,500 watt pump. So in a second is, required 1,500 joules of work to be done on your system. So there, when we subtract, we get 3,000 joules of heat delivered per second. So if you want to take a look here, the coefficient of performance in the cooling mode, and remember, for an air conditioner, your goal is not to transfer heat to your high temperature reservoir, but your goal is how much heat are you removing from your low temperature reservoir, which is what we found. So we take that 3,000 joules divided by the same amount of work which is required to, you've got to put into your machine to make it operate, which is still 1,500 joules. We find you get a coefficient of performance of 2.0. So you notice here, it's kind of interesting that for the heating mode, your coefficient of performance is 3.0, but in the cooling mode, it's only 2.0. So this is typically going to be true, that your coefficient of performance will be greater in your heating mode than in your cooling mode. All right, so a schematic diagram is one thing, but what is the physical mechanism by which, this unnatural heat transfer from a low temperature environment to a high temperature environment takes place? How is this actually accomplished? Well, let's spend a few minutes. Let's take a look at either a refrigerator or an AC unit. Okay, basically the operation is similar. We'll take a look here at the refrigerator and see how this heat transfer is accomplished. So you'll notice in the refrigerator that you have these condenser coils located on the outside of the refrigerator unit. And also notice down here you have your compressor. It's the compressor that is actually doing the work that allows this unnatural heat transfer from a low temperature to a high temperature to take place. So what's going on here? Well, this compressor, this motor works, and it compresses the gas inside these condenser coils. And this gaseous coolant is compressed. When that happens, when a gas is compressed, both its temperature and its pressure increase. And since the temperature goes up and these condenser coils are now at a higher temperature than the room temperature environment, heat is now released into the environment. And when that happens, as heat is released into the environment, this gaseous coolant now cools, and in the process of doing so, it condenses back into a liquid. All right, so that's half the picture. That's what can get rid of the heat, to the outside. Let's take a look at the cooling here. So you see this expansion valve right here. This is what comes next. So this liquid, this cooler liquid, is now allowed to, when this expansion valve opens, it is now allowed to rapidly expand into these evaporator coils on the inside of the refrigerator unit. And from our discussion of the adiabatic expansion of a gas, or any expansion of a gas, that when that happens, when that rapid expansion happens, both the pressure and the temperature drop, okay, significantly. So this rapidly expanding gas now becomes very cold, and now you see here becomes colder than the inside temperature of the refrigerator. So now these coils will now absorb heat, okay, from inside of the refrigerator. So while the condenser coils represent your high temperature reservoir, these evaporation coils on the inside of the refrigerator unit represent your low temperature reservoir. Okay, and so this rapid expansion of the liquid will allow it to, okay, become a gas. And during this expansion, as we said, the pressure and the temperature of the gas decrease, okay, so that now these coils can absorb heat from inside of the refrigerator. So you see then that this cycle then will repeat. Okay, that low pressure vapor is returned to your condenser here, okay, your compressor, sorry, in which case it will be compressed again, and the cycle will repeat. So Rudolf Julius Emanuel Clausius was a German physicist and mathematician, and you see him here in all of his splendor. He's considered one of the central founders, okay, of the science of thermodynamics. So we're going to take a look at two of the ways in which Clausius stated thermodynamics. And by the way, in our next video when we talk about entropy, he also was the first person to define or describe this concept called entropy from the macroscopic point of view. It was really, you know, Boltzmann, when he was studying statistical mechanics and kinetic molecular theory, that gave entropy you know, gave us a microscopic understanding of the concept. But Clausius was a rather important figure in the development of thermodynamics, and we're going to actually come up with two statements of the second law that he described. Okay, the first one in terms of heat flow. Okay, he says that heat does not flow spontaneously from a cold object to a hot object. And, you know, we can see that in our discussion of heat pumps and refrigerators, that it takes some work to make this happen. So this is one statement, and we can state the same basic concept in terms of a heat pump or refrigerator like this. We can say there's no such thing as a perfect refrigerator or heat pump. Some work must be done in order to transfer energy from a low temperature environment to a high temperature environment. And so when we look at the schematic diagram of a heat pump or refrigerator, saying there's no such thing as a perfect heat pump or refrigerator, okay, would mean that you could actually remove the work, so have no work, and you could transfer heat from the low temperature environment to the high temperature environment free of charge, so to speak. And what Clausius is saying is that no, okay, this concept does not exist. So in order for us to talk about the Carnot cycle later in this video, as well as the concept of entropy in the next video, we need to talk about the meaning of a reversible process as opposed to an irreversible process. So what is the criteria for a process to be considered reversible? Let's take a look. There's two criteria. First of all, the system can be returned to its initial state along the same path on a PV diagram. So to see what this means, let's take a look at a PV diagram where we have a system that starts out at some initial state, that is some initial pressure, volume, and temperature, and our system goes through some changes and ends up in a final state at a different pressure, volume, okay, and perhaps temperature. And going from that initial state to the final state, our system takes, okay, some path, which I'm showing you, okay, with this red curve right here. If this process in going from the initial state to the final state is reversible, then what we're saying is that the system can be returned to its initial state, okay, so that it must take the same path along the PV diagram. Okay, of course, it will be in the opposite direction. So if this red path represents the path from initial to final, okay, we're saying this green path, which follows the same points along the PV diagram but is in the opposite direction, okay, that path must be taken in returning to the initial state if this process can be considered reversible. And I say it doesn't mean that the system actually has to have done this. It just means that the system could be returned to its initial state along the same path. The second criteria is that the system must always be in a state of equilibrium, okay, as it's moving along this path from its initial to final state. So at all points along that path, our system must be in an equilibrium state at all points in time. And we'll talk more about that later. And if you're saying, hey, this sounds a little bit fishy here, okay, like I don't think this can really happen, well, you would be right, as we'll find out. So what are the implications of having a reversible process? What are the implications in terms of, okay, heat exchange and work being done? So if you had a reversible process, what we can say is that the heat exchange between the system and environment would be exactly the same in the forward direction as in the reverse direction. The signs would be different, but the magnitude of that amount of heat would be the same. In other words, if heat was given off by your system in the forward direction, okay, then the same amount of heat would be absorbed by your system in the reverse direction. And the same can be said about work. If you had a given amount of work done by your system on the environment in the forward direction, okay, you would have the same amount of work, okay, done on your system by the environment in the reverse direction. So once again, same magnitude in the forward and reverse direction, but the signs would be different. I think one of the best ways to see these implications here is by considering this idealized, this imaginary situation or problem we call the heat engine refrigerator combo. And we could draw it schematically something like this. What if you actually had a heat engine, which you see here on your left, and you use the work that was produced by the heat engine to actually drive your refrigerator? What would the implications be if you had a reversible process here? Well, okay, we're saying here the work produced by the heat engine could be used to operate a refrigerator such that there is no net transfer of heat into or out of the system. So notice here that if your system in the heat engine portion of the machine was to extract an amount of heat QH1, okay, from the high temperature reservoir, notice that in the refrigerator heat pump portion of your system, that exact same amount of heat, okay, would be returned to the high temperature reservoir. Okay, in other words, okay, Q sub H1 would exactly be equal to Q sub H2. We can say the same thing here. The amount of heat that would be, okay, transferred to your low temperature reservoir in the heat engine portion of the system, exactly the same amount of heat would be transferred from the low temperature reservoir, okay, in the cooling or, okay, heat pump portion of the system. So that QC1 would be exactly equal to QC2. So you can see here that given that, okay, this system could operate where there really would be absolutely no net transfer of heat into or out of the system. Okay, given this situation, there would be, the world would look exactly the same, okay, before the process as it would after the process. Now, you know, the big picture, we could state like this: when the process occurs, okay, the system and environment change. Okay, but for a reversible process, when the process is returned to its original state, there would be no evidence of any change in the system or the environment, which is basically what I just said. Okay, that because there would be no net transfer of heat, okay, then there would be absolutely no knowledge of this system having taken place, or this process having taken place in the first place. So, as you are probably imagining here, real processes are irreversible. Why is that? Okay, well, really two reasons. Okay, the two criteria that we talked about for a process to be reversible are impossibilities. First of all, friction. Okay, because of the presence of friction, this means that a process can never retrace itself on a PV diagram, since work must be done to overcome friction. Okay, there is no way that the work done in the forward direction, okay, could ever be exactly the same size or magnitude as the work done for the reverse process. Think about this. There's no such thing as a 100% efficient heat engine. You can take a given amount of work and you can completely convert it into heat. Try that. Rub your hands together. Okay, all that work you do goes into the conversion of thermal energy or heat. But you can never take a given amount of heat and convert it completely back into work in the opposite direction. The second reason that real processes are irreversible has to do with our second condition, okay, that we talked about, that at all points along the PV diagram, our system must be in a state of equilibrium at all times, okay, for both forward and reverse process. This could only happen if you had a process that occurred or took place infinitely slowly. Okay, and since no process can occur infinitely slowly, no real process can be perpetually in equilibrium, okay, at all times. So, as we see, okay, no big surprise, real processes are irreversible. It is really a question, though, of how close a real process can be to this reversibility condition. Although it is an idealization, although it is impossible in reality, some processes can mirror or mimic reversible processes. They can get close enough that, okay, as we'll see, we may get very good thermodynamic results for such processes. So it turns out that real processes are irreversible. And I think the best way to see this is through an example. So let's look at this specific example, okay, where we consider a process that consists of an isothermal compression followed by an isothermal expansion. The forward process will be the isothermal compression. So let's suppose that we have our system, we have a gas that is contained in a cylinder fitted with a piston, okay, which starts out at some initial pressure, initial volume, and temperature. Okay, and during this compression, okay, work is done to compress the gas by moving the piston downwards. So our gas, our system ends up at some final pressure, final volume, and of course the same temperature, since this is an isothermal process. So making up some numbers here, let's suppose that we do 10 joules of work in compressing the gas, and that the system, okay, the gas, loses or expels 10 joules of heat to the environment. If we now look at the reverse process, okay, which is the isothermal expansion, so let's assume that we start our system, okay, that, okay, our, initial pressure, initial volume, and temperature is really the final pressure, final volume, and temperature of where we ended up in this previous process with the compression. And let's suppose that we allow our gas to expand and do some work on the environment. Okay, so that we end up with our system at some final state, okay, final pressure, final volume, same temperature. And in this case, okay, if our system absorbs 10 joules of heat from the environment, okay, we find that the work it can do is not going to be equal to 10 joules. In other words, the work that is done by the system on the environment cannot be equal to 10 joules. Why? Okay, well, because friction between the piston and cylinder, okay, because that exists, not all of the heat absorbed will get converted into useful work. Okay, while the forward process, okay, involves a given amount of work, 10 joules of work being converted completely into heat, okay, that is allowable. Okay, the reverse process, that is saying a given amount of heat getting converted completely into work, cannot happen because of friction. Okay, so the conversion of work into heat is an irreversible process. So the last topic that we'll talk about today, okay, has to do with the work of the French scientist and engineer Carnot. So we'll talk about the Carnot engine, okay, the Carnot cycle, and Carnot's theorem. So starting with the Carnot engine, what is a Carnot engine? It is an imaginary, a theoretical heat engine that sets the upper limit to the efficiency of any real heat engine. So a Carnot engine operates through a reversible cycle. So you can see, as we just said, since no real cycle, okay, can be reversible, you can imagine how this particular reversible cycle would be the limiting case. It would set a limit, okay, to the efficiency of any heat engine operating through a real irreversible cycle. This reversible cycle is what we call the Carnot cycle, and we'll talk about that in an upcoming slide. Carnot's theorem basically says what we said in, number 1.1 above. Okay, that no real heat engine operating between two energy reservoirs can ever be more efficient than a Carnot engine operating between these same two reservoirs. So stated without proof here, okay, and to really understand what this means, we need to talk about the Carnot cycle, which we will talk about shortly. So in this slide, we will talk about each of the four processes involved in the Carnot cycle. So first of all, the Carnot cycle involves a very specific system. We're talking about an ideal gas being our working substance. And this ideal gas, as you might expect, will be fitted, will exist inside of a cylinder that is fitted with a piston. So this ideal gas will be allowed to expand and contract, okay, because of the presence of the piston. So the Carnot cycle consists of, okay, these four processes that follow each other: an isothermal expansion, which is followed by an adiabatic expansion, which is followed by an isothermal compression, and finally by an adiabatic compression. So let's talk about what's going on, okay, in our system for each of these processes, and then we'll apply the first law of thermodynamics so we can get an idea of what's happening in terms of, okay, the internal energy of our system, the heat, okay, exchange between system environment, okay, as well as the work that either is done on or by our system. So starting with the isothermal expansion, we see that the gas in the cylinder is placed in contact with a high temperature heat reservoir, okay, so that the gas can absorb heat from the reservoir, and in so doing, okay, will expand and do some work in moving the piston outwards. So very simply, this takes place at a constant temperature. It's an isothermal process, okay, but the gas will absorb heat from this high temperature reservoir, okay, will expand against the piston and do some work in the process. So the change in the internal energy of our system is zero. Remember that for an ideal gas, the internal energy is linearly proportional to the temperature. So if there is no change in temperature, by definition of isothermal expansion, there will be no change in internal energy. So that is zero. Now the heat here, okay, we'll symbolize it for this part of the process Q sub high, because heat is being absorbed by our system, okay, by the gas in contact with that high temperature reservoir. So when we add heat to the system, the sign of Q is positive, okay, according to our sign conventions. And when we apply the first law, we find out that, okay, the work done is minus Q high. This tells us, since we said Q high is positive, since heat is absorbed, that makes work negative. The way we define work, this means we have negative work done on our system, which, said another way, means we have positive work done by our system on the environment. So remember how we defined this concept of work engine before to talk about work done by the system. So as this gas expands, it does some positive work on the environment, okay, in the process. This isothermal expansion is now followed by an adiabatic expansion. And remember, for the adiabatic process, we thermally insulate our system so that no heat can be exchanged between system and environment. So the gas is thermally insulated from the environment. The gas is allowed to expand, and as the gas expands with no heat exchanged, the gas temperature drops. Okay, but during this process, the gas still does some work in moving the piston a little further outwards. So it is still an expansion. Here, because the temperature drops as the gas expands, okay, we see that the internal energy drops during this process. So the change in the internal energy should be negative. It should be less than 0. For the adiabatic process, there is no heat exchange between system and environment, so that's 0. So in other words, the change in the internal energy is exactly equal to the work done on the system. But since the change in the internal energy is negative, that means the work done on the system is negative, which means the work done by the system on the environment is positive, okay, which is exactly what we had for the isothermal expansion above. So we get positive work out of this portion of the Carnot cycle as well. So in both the isothermal expansion and the adiabatic expansion, the system does positive work on the environment. Next, we have an isothermal compression. So basically, we now put our cooled off gas, okay, in its high volume state. Since it's expanded, we now put it in contact with a low temperature reservoir, okay, and when this happens and heat now flows out of our gas into the low temperature reservoir, the gas will condense, okay, and it is compressed as energy leaves the gas and enters this low temperature reservoir. Here, once again, there's no change in temperature here because it's in contact with a heat reservoir, so the change in the internal energy is 0. In this case, since heat leaves the system, okay, Q is negative, okay, because heat is leaving the system and getting absorbed by the environment. So when we look at the first law of thermodynamics, here we find out that the work is okay, going to be positive since work is done by the environment on our system, on our gas. So in this case, positive work is done on our gas as this piston moves downwards as our gas is compressed. And finally, that isothermal compression is followed by an adiabatic compression where we once again insulate the system from the environment, don't allow any heat to be exchanged, and now the gas is compressed, okay, by some outside work, and when that happens, the gas temperature rises. Okay, so if we don't allow, if we compress a gas and don't allow any heat to be exchanged, its temperature will increase. So here we have a positive value for the change in the internal energy as the temperature goes up. Once again, it's an adiabatic process, so there's no heat exchange, Q is 0. And in this case here, we find out that the change in the internal energy, since it's positive, that means the work is positive as well, which means that work is done on our system to increase the internal energy. The environment does work on the gas. So these are the 4 processes involved in the Carnot cycle. Okay, and in the next slide, we'll take a look at what this represents on a PV diagram. So in this slide, we'll take a look at what these 4 processes look like on a PV diagram. And you may want to actually replay this slide a couple of times, because we'll take a look at a simulation that shows what's actually happening in our system and how that can be graphed on the PV diagram. So here we start. Well, okay, maybe not. I'm going to wait a second here so we can start the process at the beginning. Let me get myself a laser pointer here. All right, here we go. High temperature reservoir in contact with our gas. It expands. That is the isothermal expansion. Okay, insulated, the adiabatic expansion. Now we place it in contact with a low temperature reservoir, do some work on the system to compress it, and now we adiabatically compress it even more. So this happens pretty quickly here. Isothermal expansion, adiabatic expansion, okay, isothermal compression, followed by the adiabatic compression. So you can see that in the expansions, we get work done by our system on the environment, whereas in the compressions, we have to do work on the system. In other words, the environment, okay, does work on the system to bring about the compression. So if we take a look at what this looks like on a static diagram, okay, here we have it. You see, if we start over here at point A, we've got the isothermal expansion, followed by the adiabatic expansion here, followed by the isothermal compression, followed by the adiabatic compression. And during that isothermal expansion, we said that heat is absorbed from the high temperature reservoir, an amount we'll say Q high, and during the isothermal compression, an amount of heat QC, okay, is now expelled or released to the low temperature reservoir. So how much work gets done during the Carnot cycle? Remember, we said that for the two expansions, that is the isothermal expansion followed by the adiabatic expansion, okay, the system does work on the environment. So that's, okay, by our sign conventions defined to be negative work. Whereas for the two compressions, that is the isothermal compression followed by the adiabatic compression, okay, then we get positive work done on the system as the gas is compressed. So we get two processes giving us positive work, two processes giving us negative work. Okay, what is the overall result? Let's take a look. Graphically speaking, we can say, and we looked at this before, the work done by the system will be the area equal to the area enclosed by the cycle. So what you see here with this red area, the area enclosed there, represents the work that is done by the system, okay, on the environment. And you see here we have a positive area here, so this does tell us that work gets done by the system on the environment. So when it comes to the sign for work, okay, the total work will be less than zero, will be negative, since net work is being done by the system on the environment, and by our sign conventions, we define that work to be negative. This tells you then that the work done by the system during the expansion phases, because that's the negative work, must exceed the total work done on the system during the compression phases, because that's positive work. So overall, when we look at the net or total work done, the system does work on the environment. Okay, and if we want to look at a quantitative expression for this, and this is going to look familiar to you, we'll take a look at what the first law has to say about this. Remember that for any cycle, for any complete cycle, the change in the internal energy is zero. Okay, if we start and end in the same state, internal energy being a state function, that must be the case. So the first law looks like this, telling us that the net work is the opposite of the net heat that gets added. And when it comes to the heat exchanged, we said Q sub H, Q high, is taken in, that is added to our system from the high temperature reservoir, and Q sub C is expelled or leaves our system to the low temperature reservoir, so we define that heat to be negative. In which case, we can say the work engine, that is the work done by the system on the environment, is just the difference between, okay, the heat taken in and the heat expelled. So that tells us that the work engine is a positive quantity, and we've seen this before. So what about the efficiency of the Carnot engine? Well, we can use the expressions we derive for heat engines in general and come up with an expression for efficiency here with one caveat, which we'll talk about here. So in terms of heat, recall we said that the efficiency of any heat engine is, okay, the work that we get out of the engine, the work that the engine can do, the system can do on the environment. It's what you get out, okay, divided by what you put in, which, okay, is the heat which is being absorbed from the high temperature reservoir. Okay, we showed that the output work, okay, is equal to the difference between the heat that is absorbed from the high temperature reservoir, okay, and the heat that is expelled to the low temperature reservoir. Okay, so this expression should look very familiar. Now, and this is true for the Carnot engine. If you have a problem where you know how much heat is absorbed by your system and how much heat is expelled, okay, by your system into the low temperature reservoir, then this will do. There's also a relationship between, okay, heats absorbed and expelled and temperatures of these reservoirs, which is only true for the Carnot cycle. And for the Carnot engine, I'm going to state this here without proof. Okay, if you want to see where this comes from, then you can take a look at your text, okay, to see the derivation. But this ratio of heat expelled to the low temperature reservoir to heat absorbed by the high temperature reservoir is exactly equal to the temperature ratio of the low temperature reservoir to high temperature reservoir. So like I said, this is only true for the Carnot engine, not for any real heat engine. Okay. So when we substitute this into our expression for efficiency here, we can also get an expression for efficiency in terms of temperatures. Okay, so 1 minus QC over Q high is equal to 1 minus TC over T high using that ratio. And once again, okay, remember that this is only true for a Carnot engine. It's not true for real heat engines, okay, where we do not have a reversible cycle. As always, remember that T is a thermodynamic temperature. Okay, so anytime you're doing a problem here, you must make sure that your temperatures are Kelvin temperatures. So in looking at this, we can ask the question, what would be ways to actually increase the efficiency of not just a Carnot engine, but really any engine in general? And if you were to devise an engine, what could you do to make it run more efficiently? Okay, well, when you take a look at this expression here, this kind of tells us that you can do really two things. You can increase the temperature of the high temperature reservoir, or you can decrease the temperature of the low temperature reservoir. Now, the truth is the low temperature reservoir for a real heat engine will be determined by the environmental temperature. Okay, so in theory, your car may run a little more efficiently in the wintertime when the outside temperature is colder, okay, because you're increasing the temperature gradient between your engine and the environment. When your engine is warm, of course, not when it's cold. But basically, you don't have a lot of control over the cold temperature reservoir because that's the temperature of the environment. But increasing the temperature of the high temperature reservoir, this is something that is used in technology to increase efficiencies. One of the reasons why diesel engines run more efficiently than gasoline engines, okay, is because they are running at a higher temperature. Remember that the temperature in that cylinder for diesel engine is high enough that your fuel will ignite, okay, without the use of a spark, right? It will reach the combustion point on its own because it's operating at a higher temperature. This makes them more efficient. Under what conditions could a Carnot engine be 100% efficient? Well, when you look at it, you see here that T high would have to be at infinity. That is a physical impossibility, and this tells us that T cold, the thermodynamic temperature, would have to be 0, okay, on the other extreme. In other words, if you could make a Carnot engine that would run where your cold temperature reservoir was at absolute 0, okay, then in theory you could get a 100% efficient Carnot engine. But okay, that is impossible. Okay, you cannot, no real object can ever reach a temperature of absolute 0. So, okay, the laws of thermodynamics tell us that this is, we have these limitations on the Carnot engine. So when you look at this, if you want to know, what is the maximum efficiency you can get for a real heat engine, you can see here it's really determined by the operating temperatures, okay, of that heat engine. This ratio TC to T high, that tells the story, it tells it all. Okay, you can manipulate that ratio perhaps by your design, by your engine design, okay, but that is going to ultimately limit how efficient your engine can be. So let's take a look at a sample problem, one that would be like the type of problem you would get for a homework assignment. In this problem, we're told that a Carnot engine extracts 240 joules of heat from a high temperature reservoir during each cycle. It rejects 100 joules of heat to the low temperature reservoir at 15 degrees Celsius. Okay, so first we want to find out how much work does the engine do in one cycle. Okay, and going back a few slides, we know that the work that our system can do on the environment, okay, the work the engine can do is the difference between the heat that is absorbed and the heat that is expelled to the low temperature environment. So we're given both of these in the problem. It absorbs 240 joules, expels 100 joules. 240 minus 100 is 140 joules of work is done by our system on the environment. What is the efficiency of the engine? Okay, well, in this problem here, we're given, both Q high and QC, so we don't need to use what we know about the Carnot efficiency. We can just use what we know about the efficiency of any heat engine, okay, which is, let's calculate it by finding the output work of the engine divided by Q high. It's what you get out, the work you get out divided by what you got to put in, which is, okay, the absorption of heat from the high temperature reservoir. When we look at that ratio, we get 58.3%. So, notice that is still a lot less than 100%, right? Not only is there never going to be a 100% efficient heat engine, but what we're saying is that when you operate this engine between the temperatures here, okay, that must exist in this problem, and we don't know what they are, they're not given to us, but they are set by, okay, the description of this Carnot cycle, then for those unknown but definite temperatures, this engine can never be more than 58.3% efficient. In the last part of the problem, we're asked to find what is the temperature of the hot reservoir. Okay, well here we can, one of the ways of doing this is not the only way, but is to use, okay, this fact, this ratio between heats and temperatures for the Carnot engine. And when we use this and solve for T high, okay, we know we're given Q high, the heat absorbed is 240 joules. We just, okay, we know T cold, that's given to us in the problem. Don't forget to convert it to Kelvin. And QC, the heat expelled to the low temperature reservoir, is 100 joules. We do the number crunching, we get 691 Kelvin. So the last topic that we're going to take a look at today is how a real heat engine works. And I say here a gasoline or a diesel engine. While there are certainly some differences, the basic principle of operation is the same. And this doesn't have a whole lot to do with thermodynamics, but I think that, after taking this class, you should know the very basics of how a real heat engine operates. And I think many of you know this, so I don't mean for this slide to insult people, but I'm doubting that everybody here knows this. And since this has been a primary technology and allowing us to be mobile in society, I think it's worth knowing the very basic principles here. So let's take a look. The internal combustion engine of an automobile, we can approximate it by a reversible cycle known as the Otto cycle. Okay, I say here, unlike the Carnot cycle, the input and exhaust temperatures of the Otto cycle are not constant. Okay, so we will look at this 4-stroke gasoline engine and just kind of look at these processes here, qualitatively, of course. So what we have here, I'm showing you, does kind of go through each of these processes. Okay, the intake of the fuel, the compression of the fuel, okay, the spark and the power are very often put together as one process, where the combustion happens and as well as the expansion happens, and then finally the exhaust, okay, is the last part of the cycle, in which case the cycle can repeat. So let's just take a look at each of these phases, each of these processes, okay, involved. So starting with this process we call intake here, and you can see here in this picture, sometimes these simulations, what you see in the upper right hand portion of your screen, they move so fast it's kind of hard to follow it. So I'll show you a still shot here. So you'll see here that in your cylinder here that is fitted with this piston, okay, this is your intake valve here. It opens and allows your mixture of air and fuel to enter your cylinder. Okay, now many ways this is done. In the old days, you had a carburetor, okay, to allow this to happen. Okay, in modern internal combustion engines, you have fuel injection, okay, and it looks like here we have a fuel injector. So somehow, though, whether a carburetor or fuel injector, okay, a mixture of air and fuel is allowed to enter into your cylinder. During this phase, the piston is moving downward, okay, from the previous cycle, okay, that's not being shown here. And when the piston moves downwards, the volume of the cylinder increases, and it nicely allows this air and this fuel to, be sucked in, so to speak. And like I say here, this piston moves down because work is being done on the piston to move it downwards from the previous power stroke that's not shown. We got to start the process somewhere, so we're starting it here. Okay, so that's the intake cycle. Now for the compression. So this valve is going to close here. That valve closed, so we now have a closed system. And now this piston, from still in the same part of the cycle, instead of moving downwards, is now going to move upwards and compress the gas. So let's take a look at that. Notice that your intake valve is closed here, as well as your exhaust valve over here. So now the system moves upwards, and once again, what makes the piston move upwards is work from the previous cycle. As that piston moves upwards, the fuel-air mixture is quickly compressed. We can approximate it as an adiabatic compression. Volume decreases. This causes the temperature to go up. Now, like we said, in the case of the diesel engine, the compression is so great that the temperature rises enough to actually combust the fuel on its own. Okay, the diesel fuel reaches its combustion temperature. Okay, but in the gasoline engine, that does not happen, in which case we need a spark. That's the next phase here. Okay, so here we have the spark provided by the spark plug at the top here. Okay, and notice your valves are closed, and when the spark happens, the air-fuel mixture is ignited. Okay, and it's already at a high temperature, but once it gets ignited, okay, well, I say here there's no change in the volume because we're considering this to be instantaneous. Okay, the gas is not expanded yet, but the temperature has risen very sharply. No work is done yet because the gas has not been allowed to expand. That's why very often the spark phase and the power stroke are combined together. Okay, but within a microsecond later, okay, we now have the power stroke, right? And this combustion of the gas in the air causes this rapid expansion. This gas expands rapidly downwards on the piston doing work. Okay, and so work is done by the gas in pushing this piston downwards. And this is what, of course, is making your car move. This is where it gets its motion. This is from that power stroke. Okay, and finally, once that piston from that power stroke is now moving upwards again, okay, we see here that this exhaust valve opens and allows these combustion products, the spent fuel gas, to be expelled through your exhaust. Okay, the volume decreases. Okay, the temperature drops. Okay, and like I said, work has to be done to expel that gas. So the power stroke, work is done to expel the gas here. And now we're ready to start the cycle again. Your exhaust valve closes, your intake valve opens, and we still have, okay, that piston is still moving from the power stroke. And now you can see that we started the process over. It moves downwards, allows the fuel and air to come in, and the process repeats. So you can see here that I say most gasoline and diesel engines operate with a 4-cycle process: intake, compression, power, exhaust, in which the net work of the intake and exhaust cycles can be considered negligible. Thus, power is developed only once for every, okay, 2 revolutions of the crankshaft. All right, so we see that, we have this power stroke here, okay, but this crankshaft in the intake has moved down and the compression has moved up from the previous power stroke. Okay, then the power stroke, it moves down, and then in order to exhaust, it moves back up. So we really get, okay, that power stroke is really only a quarter of the entire process. Okay, so we really get 2 revolutions of the crankshaft in a single cycle.